In differential equations today. We've actually already dealt with these a little bit because I introduced them earlier in the microphone set up here in the good spot. We talked about these in the context of, well, in the fall. And we talked about how if I give you an equation that is dy dx equals some expression, that you can take that expression, think of it as a slope equation, and then you can plot the slopes of the equation. And then that gives you some indication of what the functions whose derivative is that equation, what that function or that family of functions looks like. Okay, so slope fields and differential equations is something that we've kind of already dealt with to an extent. So let's talk about differential equations quickly here. A differential equation is just an equation that contains a derivative in it. The order of a differential equation is just the order of the highest derivative in the equation. So a first order differential equation is just dy dx. A second order differential equation is just the second derivative of y with respect to x, and there will be 2's obviously. So that's all the order of a differential equation is. All right, so let's do a couple examples here. And in this one, we're going to find all the functions whose derivative is secant squared x plus 2x plus 5. And remember that this is really just an antiderivative problem, and we're going to do that we're going to solve this problem by taking the antiderivative. And we're phrasing it in this way: find all functions. Because of the plus c, it's a family of functions, right? There's actually an infinite number of functions technically that have this derivative. So what we'll do is we'll antiderive each part here, and so we'll get y equals tangent of x plus x squared plus 5x plus c. Right? And so that's the solution to this differential equation. When you hear that phrase, the solution to the differential equation, that's what we're talking about. All right. Now let's solve an initial value problem. An initial value problem is a problem where you're given a differential equation and you're told that the function whose derivative is given passes through a certain point. In other words, we can narrow the solution down to one specific solution to the differential equation as opposed to a family of functions or a family of solutions. So here we're given the dy dx is e to the x minus 6x squared, and we want to know the solution here. So it goes through the point 1, 0. So one way to solve this is just to antiderive, right? So you get y equals e to the x minus, it will be what, 2x cubed plus c. All right, so that's one way to solve this. And then you would just plug in 0 for y and 1 for x and solve for c accordingly. So you could finish that out, okay? I'm going to show you another way to solve this, a legitimate way to solve this as well, which is you can use the fundamental theorem of calculus to solve it. So you can take and set up an area function. So we could write y equals the integral of 1 from 1 to x of e to the t minus 6t squared dt. Right? Or and then you could say, right, well, plus c. Well, the c would have to be 0. All right, we've talked about problems like this before. So I found the lower bound because if I plug in 1 here, then the integral from 1 to 1 will be whatever this y value is, and this y value happens to be 0, so it would just be plus 0. So we've done problems like this before. So the first part of the section is not necessarily new, okay? So let's go on to the back page here. Slope fields, and we're going to talk about slope fields. And so slope fields are a graphical way of interpreting a differential equation, of sketching the slopes, or sketching the solutions to a differential equation. Now this differential equation we could solve, right? We can antiderive x and we can find the family of functions whose derivative is x. Totally possible to do. But what I want to do is show you how to make a slope field to sketch the possible solutions, because I'll show you on a simple problem, and then you'll be able to do it on more difficult problems. So dy dx equals x. Again, we're thinking of this as a slope equation. We're going to put an xy axis on here this way. All right. And then what we're going to do is take and make a table. So we'll put x, dy dx. Now you don't always need to do a table, but again, this is a method that scales. So we'll take -2. Well, we'll start at -2. So we'll go -2, -1, 0, 1, 2. And then we will go to, and then we'll graph slopes accordingly. So when x is -2, when you plug in -2 here, the slope will be -2. When you plug in -1, the slopes will be -1. When you plug in 0, you get 0, 1, and 2, and so on. Okay? So let's just start at -2. So at -2, the slopes are -2. So you're going to sketch in slopes that are steeper than -1. And those will be slopes of -2. Now, I'm not going to be super nitpicky. Your slopes of -1 should be less than the slopes of -2, but I'm not getting out a ruler to try and measure the slopes, right? And then we've got 0 at 0. And then 2 at 2. 1 at 1 and 2 at 2. All right? And so that's how you create a slope field. We're going to skip this one over here, and we're going to go right to this one here. So slope fields where we've got a differential equation in terms of x and y. Now this is an equation whose derivative is x plus y, and it's not obvious how we anti-derive this. We would have to anti-derive using implicit anti-differentiation. It's not something we've learned or talked about, or that I'm not even confident is possible. And this equation, the results will not necessarily be a function. So the slope field gives us an idea of what that equation or family of equations will look like. All right. So what I usually do for the more complicated ones is set up a table. I put the y's across the top, the x's across the side, and then I'm going to plug in each point. So for instance, I'm going to plug in -2, -2. In other words, -2 for x, -2 for y, and then perform whatever the operations are. And then for this one, I'll get -4. So that'd be a slope of -4 at the point -2, -2. So a slope of -4 is pretty steep. Okay? And then I'm going to keep going like that. So what you'll find is that across the top here, and you might even try this, pause and try it, see how it goes. But across the top, you'll get -3, -2, -1, 0. And then same thing going down here, -3, -2, -1, 0. And then you're going to get that same pattern happening. So this next row is -2, -1, 0, 1, -1, 0, excuse me, 1, 2, 0, -1, 0, 1, 2, and 3, and then 0, 1, 2, 3, 4. And then you're just going to plot all those slopes. So what you end up with plotting here is, so you've got a slope of -4, and then you've got a slope of -3, -2, -1, and then a slope of 0, I think, at -2, should be, yeah, a slope of -2, 2 is the slope of 0 there, okay? And then we've got the same kind of thing happening, so we've got -3, -2, -1, 0, and a slope of 1, right? Yeah, 1. Same kind of thing, and you can kind of just keep going, sketching slopes here. So 2, 3, 4, and then we've got 0, 1, 2, 3, and then we've got 0, 1, 2, and we've got, so this would be what, -1, 0, and 1, and you can tell I've done this problem a number of times, so I'm pretty confident in my slopes here. So that'd be -1 there, and then 0 at the end. Okay, so that's what the graph looks like, or the slope field looks like. Now the last thing that you might be asked to do is you might be asked to sketch a solution, a specific solution using the slope field. In other words, instead of asking you to solve an initial value problem where I give you the equation, which you can anti-derive, and a point on the function, or the equation, the graph of the equation, I give you a slope field and say, all right, can you sketch that specific solution given the slope field? So for instance, you might be asked to sketch the solution that goes through 0, 0. And what that entails is sort of just following the slopes to get the curve. So you can, let's go for the solution through 0, 0, let's say. Okay, so for 0, 0, you can see if you went through 0, 0, you got a slope of 0 right here. And then the graph is going to bend up. Again, I'm just sort of estimating or approximating. I'm bouncing from slope to slope to kind of get an idea of what this is going to be. And then going off to the left, I'm going to go and just kind of follow the slopes in this way. Okay, so that's what is pretty close to what the solution would be through 0, 0. Now you can improve the solution, the approximation, by improving the number of slopes that you sketch. So if we had 100 slopes sketched here, we could probably get a better picture of what that curve would be. Computer algebra systems like Wolfram Alpha and Mathematica, Maple, and even just GeoGebra will sketch a slope field for you. And you can really get a good picture of what those equations look like graphically, because you can really turn up the number of points that are graphed. But otherwise, that's pretty much it for section 1, sketching slope fields. We'll do a bunch of analysis with these, but that's the nuts and bolts of it.